As we mentioned before in a previous example, what happens when we have these matching exponents? We saw in the last problem we have these matching exponents, and we actually have to do something special when we don't have this qualification that the variables are guaranteed to be non-negative real numbers. So when we are taking a root and we have an exponent that is exactly the same on a variable, then there's a little shortcut. Since the root is canceled out by the exponent, they're the same. If I have something to the fourth power and I take the fourth root, we're just undoing itself on that operation. We can actually just kind of cancel it out, and we just have the radicand. However, if our value for n, the exponent and the index, are even, then what we have to do is take the absolute value of the radicand. Because recall that we cannot have a negative solution to a square root. However, if they're odd, if n is odd, then we can just cancel out, take the radicand, and we have our simplified solution. No absolute value necessary. And so we see the difference here in that we have to make the assumption that variables can represent any real number. So we need to make sure we include absolute values. And let's go through an example of why we have to include those. So for example, let's work this out the long way. Let's say, okay, let me go ahead and square -4. So that's -4 times -4, which equals a positive 16, and we square root and we get 4. But if we use the rule with finding the nth root of a to the n, and we say, okay, well, this radical is canceled out by this exponent, we're left with -4. Well, these are different answers. -4 does not equal 4. That's where the absolute value comes in. Once we take the absolute value, we're left with just a positive 4. Well, let's think why we do this. Why do we just arbitrarily say absolute value? Well, consider what happens whenever we square something. Whenever we multiply something by itself, the result is always positive. Whenever we take an absolute value, the result is always positive. So by applying the absolute value, we're adding in the feature that, well, this has to be positive because I'm raising it to an even power. And that ensures that we get the correct solution. Now, here I can't just take x to the -3, raise it to the 6th power, have this long polynomial. So in order to take the exponent and cancel out the radical, we can simplify it, but we're left with x minus 3. Now we have to consider, well, x can be anything. X can be any real number. Variables represent any real number, and negative numbers are real. Well, what if x was something like -5? Well, then I'd have a negative solution. -5 minus 5 is -8, and I can't have that. And so since x can represent any real number, we have to put it in absolute value and leave it in absolute value so that if x is something like -5, then when we evaluate, we end up with a positive solution. And so we have to make sure that we consider the fact that that variable is still part of the expression. Now here our index and our exponents are odd, so you can cancel them out and we can have a negative solution on an odd index. So we don't need absolute value. Same with 7th root and the expression to the 7th power. We have 3x minus 5, no need for absolute value. Now when we look at e, we can take the square root, and I have 7x, and we have absolute values because they are even. But keep in mind that 49 is not a variable and 7 is not a variable. And so we'll go into more detail about this later, but it has to do with the product rule of radical expressions, which is very similar to the product rule of our exponential expressions. And what this means is that, well, since 7 is a factor of x, we don't need to keep 7 in the absolute value. We could write it as separate absolute values, and the absolute value of 7 is just 7. So we can take the absolute value. However, x needs to remain inside the absolute value. Note, we did not do that with example B, because -3 is not a factor, it's a term. And so it has to remain attached. We cannot apply a product rule because it's not a product, it is a term. So that subtraction sign keeps them glued together inside the absolute value. Here we have a polynomial, and hopefully by now your first instinct when we have a polynomial is to factor it. Well, if you notice, we have a perfect square trinomial, so x plus 2 squared is the factored version, which now allows us to cancel these out. Because it's even, it needs to be in absolute value bars.